morning, everyone. I'm Dr. Yasha Tayal. Here I'm going to give a video series for superconductivity. In the previous series, we have taken a number of topics of superconductivity. We talked about H. Camerling Ons, who observed superconductivity in the year 1911, who talked about that resistance drops zero when temperature is cooled to very low region, so the current can freely pass. So the first observation was for mercury. For mercury, he observed that resistance, which was above critical temperature 0.08 ohms, reduced to 10 per minus 6 ohms below critical temperature. So for pure materials, critical temperature was quite low, but if we use a combination of number of materials, alloys, then this critical temperature can be raised. We studied about the behavior of this critical magnetic field over the temperature. Meissner effect shows that when a specimen is placed in external magnetic field below critical temperature, no field lines are allowed to pass. So this actually shows the diamagnetic behavior in superconductors. Persistent current talks about if we take a hollow specimen and the external field is removed below critical temperature, then these field lines are trapped forever, which leads to generation of persistent current. So Silsby's rules talks about behavior of current, critical current on the critical field. Then we talk about types of superconductors. There are two types of superconductors on the basis of magnetism. If the magnetic field is quite low, the elements are type 1 superconductors. At high magnetic field, they lose away their superconductivity behavior. So they exhibit perfect diamagnetism, and Meissner effect is totally obeyed below HC. Now for type 2 superconductors, materials hold superconductivity property even at very high temperature. So there is two types of region in it, for which shows perfect magnetism Meissner effect, and the region which shows partial obey of Meissner effect. So that is the vortex in the mixed state. And above SC2, we have normal behavior. So these are the two types here which we had. Now, if we, this is the graph which shows the behavior of the types of superconductors with respect to temperature. We studied about properties of superconductor, properties which shows how critical temperature or critical magnetic field or critical current are related. Isotope effect, very important property, which talks about the basic mechanism happening in the superconductors, how the phonon field is important. So if for a particular compound, and if it has isotopic mass, its critical temperature will vary with the isotopic mass. So this gives an insight towards the dependency of critical temperature on the isotopic mass, as well as the lattice vibration generating in that specimen. Entropy, as we all know that entropy should be least. So here we have very low entropy, which means the super electrons are highly ordered. Thermal conductivity, as super electron does not show any resistance, so they won't be able to transport energy from one part of the system to the other part of system. Specific heat is again a very important property in this particular system. So specific heat, we studied that it depends upon a function of temperature, which is known as energy gap. And this energy gap formula is exponential minus delta by kBT, kB Boltzmann constant. Now this delta depends upon critical temperature, which means that it is a specimen dependent function. So delta basically tells about it is the gap between normal electrons and super electrons. So the gap between normal electrons and super electron constitute the delta, which is the energy gap. So specific heat, it is the heat or amount of energy needed to raise the temperature by 1 Kelvin. So definitely for superconductor, this value will be very, very low. Now we're gonna address certain numericals from this topic. So certain numericals which I would like to address from this topics goes are, very first numerical I would like to address from your isotope effect. The critical temperature symbolizes Tc for a specimen as mercury with isotope 199.5, atomic mass unit is 4.185 Kelvin. Calculate the critical temperature when its isotopic mass changes to 203.4 atomic mass unit. So in this question, the thing which we have to address carefully is that the temperature, critical temperature is 4.185 Kelvin for mercury, which has an isotopic mass of 199.5 units. Now they're saying that we are having a element which is having two types of mercury. The other mercury is having mass 203.4 unit. So now what the temperature, critical temperature will be for this type of mercury. So as per the isotope effect, we have the formula as critical temperature is m to the power half constant. As we've addressed, Tc is proportional to m to the power minus half. So we're going to have this form. Now as we're having two series, so the formula which we're going to use is this one. So from here, Tc2 formula can be written as substitute the values here. We no need to change the units because these will be cancelled out. We're going to solve this value. Our answer will be 4.145 Kelvin. So this is the isotopic, this is the critical temperature for mercury when its isotopic mass is 203.4 units. Very important numerical. Next numerical which I would like to address, that is on the property of temperature dependencies of critical magnetic field. Here the specimen we're going to take as tin, a super conducting tin has a critical temperature of 3.7 Kelvin at zero magnetic field. And a critical magnetic field 0.0306 Tesla at 0 Kelvin. Find the critical magnetic field at 2 Kelvin. First, we need to understand the question. For tin, critical temperature is 3.7 Kelvin. And the critical magnetic field at 0 Kelvin. Critical magnetic field at 0 Kelvin. So here Hc is a function of temperature and temperature is 0 Kelvin. So for that magnetic field is 0.0306 Tesla. So we have to find, spelling I've written bit wrong, find the critical magnetic field when the temperature is 2 Kelvin. So the formula for this particular part goes in this form. I'm going to substitute the values. When we're going to solve this value, what we're going to find is 1 minus 0.2922. I'm going to solve this. 1 minus it will lead to 0.7078. And the answer will be 0.0217 Tesla. So this critical magnetic field is at 2 Kelvin. So this value is less than the value at 0 Kelvin. So as we move away from 0 Kelvin, the critical magnetic field value will reduce. So now, next we're going to use is the next numerical again, which is very important. I'm going to use here is calculate the critical current and critical current density for, so we're going to take a different material. Previously we took mercury and tin. Now I'm going to take, say for example, lead of diameter 1 millimeter at 4.2 Kelvin. The critical temperature for lead is 7.18 Kelvin and critical magnetic field at 0 Kelvin is 6.5 into 10 to the power 4 amperes per meter. Quickly going to understand. Here the critical temperature for lead is, critical temperature is 7.18 Kelvin. While critical magnetic field at 0 Kelvin is 6.5 into 10 to the power 4 amperes per meter. We have to determine critical current. So formula for this is 2 pi r Hc. But this is Hc or this is Hc0. This is actually HCT. So we have to determine critical current at 4.2 Kelvin. So this is our operating temperature. So at 4.2 Kelvin, we have to determine IC, which means that this field cannot be the field at 0 Kelvin. So first we need to determine the field at 0 at 4.2 Kelvin. So for that we have to make use of this formula. And through this formula, we're going to keep the values. So we're going to solve this value. This value is evaluated as 4.276 into 10 to the power 4 amperes per meter. So this is going to value, this is the value we're going to obtain. Now we're going to substitute this value in our formula of 2 pi r Hc. In this particular question, diameter is given as 1 millimeter. So the radius can be written as 0.5 millimeter, or if you're going to convert it into centimeters or say meter, the value will be 10 to the power minus 3 meter because we have field in meter. So we're going to substitute the value 2 into 22 by 7. R is 0.5 into 10 to the power minus 3. Hc is 4.276 into 10 to the power 4. So this will result in 134.3 amperes. Again, we have to determine critical current density. So in order to determine the critical current density, we need critical current density. This can be as current upon area. So the value will be 134.3 upon pi r square. We will solve this and obtain the value as 1.71 into 10 to the power 8 amperes per meter square. This is the value of current, and here is the value of critical current density. Very important numerical. Students do mistake is that in the formula of IC, this simply applies the formula of HC0. It's not HC0. Current has to be determined at 4.2 Kelvin. So the field should be taken also taken of 4.2 Kelvin. So now to evaluate HCT, you have to use a basic formula, right? Then only can be able to solve it. So I hope so. The 3 numericals I have taken today. One on the isotope effect. If the mass is varying irrespective of the element, its atomic number remains same, critical temperature will vary. Hence, we have proved here. Again, the basic concept, if temperature is varying, critical magnetic field varies. At 0 Kelvin, we have maximum magnetic field, and as temperature is increased, so we are having lower magnetic field. Now, critical current density, we have to carefully keep the magnetic field. We have to determine critical current density at 0 Kelvin or at an operating temperature or at critical temperature. Critical current density is simply current upon area. So the references for this content are Solid State Physics by Supillai and Concept of Modern Physics by Arthur Pfizer. I hope so this video finds useful for you. Thank you so much for patiently watching this video. Keep tuned with us for watching the next videos on this superconductivity series.